this session at 2 o'clock Eastern time. This time we're going to have very, happy to have Holly Cummings, currently a Red Hat principal lead engineer there. And I used to work with Holly too back in IBM. So happy to see her here. And she's going to be talking about making your applications green. And that's something too I'm really interested in as well. I think this is probably about the only talk about sustainability. Most of the time, when I talk about things, the sustainability usually is kind of underneath the hood, right? I'm talking about, okay, let's cut the cost. The cost is directly related to like green, it's all of these things because you get charged. But anyway, without further ado, the stage is all yours. Holly, welcome.
Thanks so much, Mary. And, like you, I think this is a topic quite close to my heart. And actually, I think it's something that should be quite close to all of our hearts working in IT, because the IT industry has quite a large carbon footprint, and we're responsible for quite a lot of the world's, well, a significant proportion of the world's carbon emissions. And to sort of give a sense of scale, when we think about, carbon bad guys, planes and flying are kind of the poster child of irresponsible carbon. But the digital world, which means IT and also things like our home computers, that creates more carbon emissions than aviation. So we really do need to be looking at ourselves. And in that figure, the sort of the digital world, I mentioned that does include things beyond just core IT, like what most of us do for our day jobs. But what if we look at just core IT and even narrow it down further just to data centers? That footprint is still pretty large. So data centers use as much electricity as a medium country. So they use a little bit more than South Korea, a little bit less than the UK. It's a lot. And if you include also the network traffic in and out of the data centers, which I think you kind of have to, that's part of the workload, then we are definitely, we're sort of starting to creep up to like a mediumly large country. Like at that point, we're more than Brazil. So this is kind of a bit depressing. And I think it's sort of easy to feel a lot of despair about the climate. And then it's easy to feel a lot of despair about our role in that. I don't think that's helpful or productive. And I think in a weird way, it's actually kind of good news that we have such a large role to play in the climate conversation, because that means that there's something that we can do. We have power to make change. And so instead of kind of succumbing to despair, I really like to instead, be a solutionist. Let's think about what we should do, because it's sort of obvious, but like solutions are the solution. There are solutions out there. There are solutions out there that are already making a big difference. And so we have a part to play. So then the question is, okay, yeah, but what should we do? And I think we can narrow that question down a little bit more to, should we reduce our carbon footprint? Should we reduce our greenhouse gases? And the answer is, yes. For a lot of reasons. One reason is that it is the right thing to do. But if that's not enough, and hopefully it is enough, but if that's not enough, there are a lot of business benefits as well to reducing that carbon footprint. One thing is, as Mary mentioned at the beginning, lower greenhouse gas emission is almost always lower costs. So why wouldn't you? But then there's a second benefit as well, which is that if you have that sustainability in your business, then you score higher on ESG metrics. And that's something that a lot of businesses are looking at. So a survey was done recently, and sustainability was the number 2 priority for CIOs, right behind operational efficiency. And half of European organizations include ESG criteria in their vendor selection process. So this is something that's going to give you a competitive advantage. And it's not just about selling your product, it's also, of course, about talent and do people want to work for your business? And if your business is doing the right thing, people are more likely to want to work for your business. So it helps all round. So then the next question is, okay, but how, what are the practical steps that I should be taking as a software engineer, as someone working in IT? This is something that our industry is starting to think about a lot. A really good entry point to the conversation, I think, is the Principles of Green Software Engineering. So you can visit it, principles.green. There's a website. There's a lot of text on the website. There's about 9 things to consider when trying to design a green architecture. But like I said, it's a lot of words. I don't find it totally intuitive. So what I try to do is I try to take all of those words and turn them into a picture. And then I sort of tried to put some higher level categories in as well on these sort of 9 points. But you can see from this, it's still a lot. So this is quite a complete model, but I don't know about you, but I can't actually hold it all in my head. It's a bit overwhelming. And of course, being overwhelmed by it all is the problem that we're trying to fix. I think we need some sort of easier entry points. So certainly how I hold it in my head is I simplify this down even further. And so the first thing to look at when trying to make your Java application greener is the electricity source. Quite a lot of the world's electricity is still generated by burning coal, which is obviously a fossil fuel. It's an extremely high carbon fossil fuel. A lot of the rest of the electricity is generated by burning natural gas, which is slightly less carbon intensive, but let's face it, it's still a fossil fuel. And what determines the electricity mix for your workload is more or less where your workload is running. The location, each location has sort of a characteristic energy mix, a characteristic set of ways that it generates electricity. And so if you relocate your workload, you can often lower your carbon footprint hugely with almost no effort at all. So here I've drawn sort of, a rough little approximation. That's not really going to be precise enough to make a decision. But what you can do is you can go to resources like electricity maps, and they show you a historical energy mix for each region. And you can see there is a huge variation. So if you look at some of the Nordics countries, they're 100% low carbon and 100% renewable, which is pretty amazing. Interestingly, Quebec also is 100% renewable. Ontario is quite high proportion low carbon, but some of that is nuclear, so it's not renewable. But you can see, there's some pretty green areas, and there's also some areas that are really not at all green. A lot of the energy is coming from coal. A lot of the energy is coming from fossil fuels. And in particular, it's not really broken out on that map, but Virginia is a little bit of a concern. The transatlantic pipe that carries data from Europe to the US goes in via Virginia. And Virginia also has a lot of coal. So Virginia is a really natural place to build data centers because you've got the data and you've got the electricity. But then, of course, it becomes a little bit of a problem because that electricity is coming from coal, which is not ideal. So what we sort of need to do is try and either shift the location or shift the energy mix. So I'm just going to pause. I can see we've got a question about the link for the Principles of Green Software Engineering. I think it's principles.green, but certainly if you search for Principles of Green Software Engineering, you'll find it. And also I'll share a link afterwards. So one of the things with Virginia is that the power provider in Virginia, Dominion, has historically been quite reluctant to introduce renewables in the mix. That is shifting now. It's getting better, but it is still not a green place to run workloads. So it definitely, if you're running in the cloud, or even if you're running in any kind of data center, look at the sustainability information before you choose your hosting region. And as well, like, sometimes that information is easy to find. Sometimes you have to really dig and then look at external energy mixes. Choose a cloud provider who makes it easy, because this stuff matters. The other thing that matters is the time of day when you run your workload. One of the things that I think has caused a lot of angst about renewable energy, and it's made it harder to incorporate, is that it tends to be that if you have something that's burning fossil fuels, you can just run that plant 24 hours a day and you will get the same energy output. If you're relying on something like solar or something like wind, that capacity fluctuates. I mean, obviously, in the day the sun shines, at night the sun doesn't shine. For wind, it tends to be reversed. But in both cases, you've got times when you've got electricity and there's times when you don't, which isn't so good for a 24/7 globalized society. So that's something that we sort of maybe need to shift our workloads to follow the sun or follow the wind or that kind of thing. The other thing that makes a difference is how much load there is on the grid. So if you're running your workload at the same time as everybody else, if there's a shortfall in capacity, there just isn't enough sun, there just isn't enough wind, that shortfall has to be made up by increasing how much is being generated from the fossil fuel plants, because those ones it tends to be easy to scale up the capacity. Whereas with a solar farm, it gives you as much as it gives you. So what we're starting to see now is something that we call carbon aware. And so what this is trying to make sure that you run your workload in the right region at the right time to make sure that your carbon footprint is as low as possible. So it's the same workload, but you're running it in a smart way. So this is a data problem. You need to have the information about what the energy mix is. You need to have the information about, as well, what are your requirements for this? Does it need to be run now, or could it be batched? Do I need low latency, or is it okay if I have a bit of a lag because I'm running in a region far away? So it's also, as well as a data problem, it's an orchestration problem. And so this is something that I think hopefully increasingly cloud providers are going to be providing this service. It's something that you kind of want to have as a service that, is transparent to you with maybe a minimal bit of input. So there's now something called the Carbon Aware SDK. And so we're seeing, again, this is something that's still an emerging area. And we're starting to see, again, carbon aware dispatching being provided by some cloud providers. So it's something that hopefully we'll see more progress in this area. And it's something to look out for. So that's the sort of the first step. And then the second step, I like to think of in terms of the 4 vowels. So all of the stuff about relocating your workload to the greenest area and running it at the greenest time of day, that's all assuming your workload stays the same. But then there's a question about, like, should the workload stay the same? Probably not. So when we think about our workload and what we can do in terms of our workload, the first thing that we want to look at probably is sort of hardware and infrastructure. So the first thing to look at is elasticity. So that's how easily you can scale your workload up and down. The second thing is utilization, which is how much of this computer's capacity am I using? Am I making good use of this computer, or have I just bought something that's sitting idle? The next thing to think about is your code. Is the code efficient? Can we make the algorithm use fewer CPU cycles. And then the last thing is about people. And really, it's about utility. Is this thing we're running useful? Should we even be running this code? And often the answer is no. And an example of this, for example, is quite a lot of us, if we want to listen to a song, we know that we can find the video for that song on YouTube. So we go to YouTube, we click play on the video. We don't watch the video because it's in the background. We're doing other things. We're just listening to the song. But it's the video streaming that uses the vast majority of the energy for listening to that song. So really, we shouldn't have even been doing it. It gave us no value at all, and yet it had a cost. And of course, these things sort of are interrelated. And so, for example, when we think about elasticity, the reason we want elasticity is so we can maximize the usefulness. And if we're not using something, we should turn it off because we're not using it. And I started thinking about this a few years ago because I saw a talk at the Chicago DevOps Days by Jeff Dark and Nerdy on Twitter. And he said that they'd done a little bit of scripting because they used to leave their applications running all the time, like many of us. And they wrote a little script that turned them off at night and turned them on in the morning, and they reduced their cloud bill by 30%, which is a huge saving from a little script. If any of you know Tom Cools, he was telling me a story as well that his wife was working in the IT department in a school, and she wrote a little script to turn the computers off overnight. And she worked out that it saved the school 12,000 euros. That's a huge sum of money that can be used for something useful by turning off computers that no one was even using. And we like to imagine that in the cloud, we have good elasticity, and we kind of do. At a technical level, at a low level, that elasticity is there. But in practice, we tend to use the elasticity to scale up, and we're much less good at using the elasticity to scale down. And this is a people problem, and it's also a technology problem. So if you look at Kubernetes autoscaling, for example, the algorithms tend to be optimized to making sure your users don't get errors. And so they're really eager to scale up, and they're pretty reluctant to scale down. So it's good, but it's not necessarily going to save carbon in the way that you hope. And I love this observation from Corey Quinn. And he said, the beauty of cloud is in its elasticity. Yep, we've all heard that lots. It lets you scale up to meet traffic demands. And then when that traffic wanes, you can keep your scaled up environment running in perpetuity to help send some engineers' kids to college. And we've all done it, right? And I can quantify how much we've all done it as well. So I hear a lot of anecdotes about this. I went to visit a client recently, and they were telling me that they keep pretty much all of their infrastructure is running all of the time. And some of their infrastructure they kept up all week just to run batch jobs at the weekend. And then they had other things that were only used during working hours, but it was up all week. And, that's bad when it's only used some of the time. But there's a worse side too, which is a lot of workloads, they're not used some of the time. They are used none of the time. And so in 2017, someone set out to research this, and they looked at 16,000 servers. So quite a big sample. They found 25% of them, a quarter of them, were doing no useful work. And they tried to figure out, how did this happen? Why is there so much waste? And the best thing that they could come up with was perhaps someone forgot to turn them off, which is just so sad. But again, I think it's easy to sort of look at other people and say, wow, why don't they turn off their workloads? But it is scary to turn off applications. It used to be that when we turned applications off, we were quite worried that they wouldn't come up again. After a site power outage, there was always this thing of like, are the workloads going to come back up? And there was always one or two that just didn't come back up for some reason. So then they had to be kind of nursed back into health. And of course, that takes time. But then there's also sort of a question of, I think this workload isn't being used. Am I 100% sure that this workload is not being used? Well, maybe. And so we sometimes talk about the scream test. And the scream test is that you turn the workload off and you see if anybody screams. That, of course, can have some reputation risks depending who is screaming. And I heard a story recently. So it was the CIO of a strategic outsourcing company, quite a large company. And they realized that they had a ton of internal inefficiency. So they did sort of a trawl through their infrastructure, their internal infrastructure, to find applications that weren't being used. And there was this one box, and they couldn't figure out what it was doing. Nobody claimed the application on it. So they were like, okay, let's turn it off. It turned out the reason they couldn't find anybody internally who owned this box was because it wasn't being used by someone internal. It was providing the whole network backbone for one of their customers. And somehow this box had been like completely misallocated and assigned as internal when it was like the internet for one of their customers. So that was a slightly awkward conversation. But I think as an industry, we need to get away from, if we're going to solve this problem, we need to get away from that kind of instinctive, I mustn't turn the application off because what if something terrible happens, and towards a model which is more like a light switch. So I think a light switch is the ultimate elasticity. None of us ever worry about turning off the light switches in our house in case it doesn't come back up. We do it all the time. We do it instinctively. Some of us automate it. Most of us do it manually, but it's so easy. We just go for a flick and it's sorted. And then when we need the light, we turn it back on. And I think as an industry, we have to move towards that same experience for our workloads. So it has to be that you can turn it off and on again, and it has to be fast. You can't be waiting for it to come back up. It has to actually work when it comes back up. And so that means that you need to have idempotency, so it behaves the same for repeated requests. It needs to have that resiliency. And this goal of being able to have things that come up and down reliably and quickly, I call it light switch ops. So far, I'm the only person who calls it light switch ops, but I keep waiting that, someday the term is going to catch on. Because I think it is really important, and it saves carbon and it saves all sorts of other things. So the next thing that we need to look at is the efficiency of our applications. Now that we've sorted out only running the application when it needs to run, how can we make the most of that time? And an obvious place to start when we think about this is looking at programming languages. And so, of course, people have looked into researching what programming languages use the least energy. And the corollary of that is what programming languages use the most energy, and so that we can laugh at them. So this is the paper that looks at it. I won't make you read the whole paper. I will summarize the answers. And it looks like this. So the normalized efficiency, we have Python is truly atrocious, which is kind of interesting because it runs some very heavy workloads in quite a lot of the industry. JavaScript, I think as Java engineers, we have a natural tendency to laugh at JavaScript, but JavaScript isn't bad. And particularly for some workloads, it can be pretty efficient. But as we probably would expect, C is pretty amazing, Rust is pretty amazing. Java isn't bad. And Java actually does better than a lot of compiled languages, even though it's sort of an interpreted language. So this is the actual table. And if you look just at Java, it's 5th out of about 20, which I think is quite respectable. But you can see Java is about 2 and C is about 1. So Java is about half as efficient as C. But there's some variability in that because how we run the JVM itself as well can make a huge difference to the energy consumption. So some people did research on just looking at different JVMs, different GC settings, different config options, and they found that depending how you configured it, you could double the consumption, which means depending how you configure it, you can halve the consumption, which is kind of worth knowing and worth thinking about. And so then the next question is, so if just the JVM parameter is my choice of GC, that kind of thing, a little bit of tuning can make a factor of 2 difference. Does the framework I use make a difference? So I work on Quarkus, and Quarkus has a lot of great things about it: developer joy, wonderful user experience, designed for the cloud, all sorts of good things. But one of the things that a lot of people know about Quarkus is its performance is pretty amazing. So it uses very little memory, and it starts up very fast. And it's not on this chart, but it also has really quite impressive throughput, sort of industry-beating throughput. So we kind of intuitively felt like if Quarkus is so small and so fast, does that mean it has a small footprint? And we kind of intuitively thought it did, but we didn't have the measurements for it. Turns out measuring carbon is kind of hard. The steps are simple in theory, but there's sort of lots of places to stumble. So if you want to measure your carbon, which is of course the first step to reducing your carbon, the starting point is that you measure your power usage. And so you can do this just by looking at what's coming out of the wall into your computer. This is quite complete. It tells you all of the power that your equipment is using, but it only works if you actually have physical access to the wall. And you need the right specialized equipment to do that power measurement. And of course, it's sort of very manual as well. You do the measurement and then you write it down, which is a bit. So instead, a lot of CPU architectures have some built-in way of measuring it. So for example, with Intel, there's a tool called RAPL. This is really nice because you can just put it into your normal benchmarking flow. The downside is it doesn't get everything. So it misses some parts of what's going on in the CPU just because of the limitation of the tool. And it definitely misses the impact of the network and the network traffic. And of course, network traffic data costs a lot of carbon because as that data moves through the internet, it passes through a bunch of switches. Switches are computers. So we kind of need to take that into account. But probably the most significant problem with RAPL is that it just assumes that you don't need access to the wall, but you still do need access at a fairly low level to the computer. And if we're running our workloads in the cloud, that computer is a black box. We don't have access to it by design. That's kind of the point of the cloud. So in those cases, the best that we can do to try and work out the carbon consumption or the power consumption is to look at the load. The good news is there's now data sets available which allow us to map from that load to a pretty good estimate of how much power it was using at the wall. Once we have that estimate, then we can convert that power usage to a carbon measurement. And that's going to depend a lot on whether it's coal or wind or solar or what the energy is. To figure that out, we can look at the published energy mixes for each region. It's still not perfect. There's some methodologies that are being introduced to do this. Usually each cloud provider will have one, but the methodologies, most of them aren't open. They're not consistent. So if you're looking at different cloud providers, you can't necessarily compare it. But it's a start. And the third thing that you need to look at is the hardware that you're running on, because that manufacturing hardware has an enormous carbon cost. And so we need to consider that embedded carbon. That's kind of complicated. The good news is there are simpler models that we can use. One model that I'm increasingly fond of is what I call the vroom model. You can probably tell I made up that name. And this is interesting. If you go back to that table I showed for the programming language comparisons, where they looked at the power consumption, and that second column is the total time it took to run the workload. And you can see those two columns are almost exactly the same. The relative position of each language is almost exactly the same. So if your program runs fast, it's going to use less carbon. That efficiency of execution translates into carbon efficiency. So as a rule of thumb, energy consumption, if you're using the same resources and you haven't just doubled your throughput by adding two computers, energy consumption is kind of proportional to execution time. Another model that can be quite useful is the economic model, or the full name for this is the Economic Input-Output Lifecycle Assessment, but that's a mouthful, so I would recommend you call it the economic model. And if we sort of distill the economic model down, what it tells us is that if you reduce your cloud spend, so that means both the electricity bill, the hardware spend, all of those things, you're probably reducing your carbon footprint. Again, if you keep other factors the same. So when I talk about these models, the sort of the vroom model and the economic model, and what, this idea of using cost or performance as a proxy for carbon, people who know this field well, I can sort of see them in the corner of the room kind of clutching their heart and going, stop, stop, stop. Because it is kind of wrong. Or at least it's sometimes wrong. But we all have other things to be doing. We're not going to spend our whole life measuring carbon. Someone should be doing that, but not us. So we do need these heuristics to allow us to do the right thing while getting on with other things. So for me, accept the limitations of these models, but find them useful. So that was a long digression. Let's go back and talk about Quarkus. When we measured Quarkus, what did we find? We can sort of start with the economic model, because a couple of years ago, a colleague of mine did some cost analysis for Quarkus. So he took a Quarkus application, he took the equivalent application on another framework, and he wanted to do a real live test. So he ran this application for 20 days while he fired a steady load at it for 20 days. So this wasn't, just I ran my application for 10 minutes, here's what happened. It was, okay, over the lifetime of, a decent chunk of work, what happened? What did I see? And so he ran the application on the smallest instance where it could run without getting errors. And you can see that for the legacy framework, the smallest he could go was T2 medium. For Quarkus on JVM and Quarkus native, he was able to go to a T2 micro. And so that you can see on the axis, the cost. So it was over $30 for the legacy framework. It was under 10 for Quarkus. So saving money. Cool. We can go from that cost experiment and using that data set that allows us to look at the instance and work out a carbon footprint. We can then fill in some estimates for carbon footprint. And what we see is they're kind of proportional, as we'd expect because of the economic model. So on the T2 medium, the carbon footprint was about double what it was on the T2 micros. So using Quarkus cut the carbon by about half. The granularity of the instances can't show it because I can't allocate a T2 micro but make it 127 meg of RAM instead of 128. But what we saw in that experiment, just like seeing how the error rates, is intuitively it feels like native probably has a slightly smaller carbon footprint for that load. So with those experiments, we kind of had to like the granularity of the instances and the granularity of the load measurements meant it was an estimate. You can kind of get the idea, but it's an estimate. But we wanted to be more precise. So we did another set of experiments on a machine that wasn't in the cloud. It was a machine that we had in front of us, so we could use the actual CPU measurements to get the power consumption and the carbon consumption. What we saw in those experiments is pretty similar, which is kind of reassuring. So what this chart is showing you is basically that the top lines are bad and the bottom lines are good. So the top lines are showing that it's using more carbon, and along the bottom we're showing how many requests per second we injected, and you can see that some of the lines kind of die early. So for example, when we took the legacy framework and we ran it as a native application, it could only go up to about 7,000 or 8,000 requests per second. And then it just went, I have had enough. I'm not going to do more than 7,000 requests per second, no matter how much we injected in. And it used quite a lot of carbon in order to do that. So the order is legacy on native used the most carbon. Legacy on JVM was next. Quarkus on native was next. So Quarkus on native used less carbon than the legacy on JVM, but more carbon than Quarkus on JVM. And that was kind of a single instance, so a low load. What if instead of handling 20,000 requests per second, I want to handle 100,000 requests per second? At that point, I need to do some parallelism. I need to scale horizontally. And this gives us kind of a neater chart, but the story is exactly the same. Legacy framework on native used the most carbon to handle the load. Quarkus on JVM used the least carbon to handle the load. So the conclusion from that is pretty similar. So Quarkus cuts carbon by a factor of 2 or 3. One thing that's sort of surprising, and I'll come back to this, is that running as a native application, even though it has a tiny footprint and starts up really fast, it consumes, for this kind of workload, more carbon than running as a JVM application. So I'll come back to that, but let me just answer the main question, that starting question, which was, does using Quarkus reduce your carbon emissions? And the answer is, yeah, absolutely it does. Without doing any sort of extra anything, Quarkus kind of automatically saves you time because it's faster, it's got that higher throughput. It saves you money if you're running on the cloud, and it saves you carbon. It will about halve the carbon footprint of the workload, which is pretty cool. I said I would come back to native. And this is one of the things that I get asked about the most. Let me sort of start with a little bit of a reminder of when should I run my application in general as a natively compiled binary? When does that make sense? So I'm using Graal JVM to do ahead of time compilation. The use case for that is if my workload is pretty low, so throughput isn't the bottleneck, native can be a great choice. If I'm running on old hardware, if I want to run on a Raspberry Pi, if I want to run on a micro instance on the cloud, if I'm really tight on memory, native is going to make a lot of sense. If I'm redeploying this application really often, if I'm doing continuous delivery, and sometimes, we see that with continuous delivery, an application might get redeployed every 5 minutes. For a Java application, it will probably never get properly warmed up before it gets spun down. So then native is a great choice. And of course, the classic use case for native is serverless. So JVM, on the other hand, makes sense. If your workload is high, you need a lot of throughput, native is a good choice. If your processes stay up for a long time, then you've got time to warm up. And starting really rapidly, starting in 0.01 seconds doesn't save you time because you're going to be running for a week. And again, if your workload is pretty stable, and so you don't need much elasticity, you're not going to take advantage of an underlying orchestration to spin it up and down, native is a good choice. So that's just in general. But what if you want to optimize carbon? Well, the answer is exactly the same. So the sort of the use cases for lowering carbon end up being almost exactly the same as the general use cases for native. So if you optimize your cost and if you optimize your application performance, you're almost certainly also optimizing carbon. One of the nice things about Quarkus in particular is that native versus JVM, we sort of talk about, like, should I be native? Should I be JVM? It is totally not an either or. One of the things that we like to recommend is a hybrid deployment model. So you have sort of a core that's running on JVM to get that really high throughput, but then you can do, like the equivalent of cloud bursting, but JVM bursting. So then you have native applications that if you get a spike in load, you can bring those online really quick. Another thing I want to mention about native is that I saw a demo a while ago, and it was so cool that I've just been talking about it ever since, where a colleague was using Quarkus for a CLI. And because it starts so fast, he was actually able to get it to do things like command completion with a Java application as a CLI, and it was imperceptible. So although we talk about native a lot of the time for serverless, native isn't just for serverless. There are all sorts of other applications where native can really allow you to do something that you couldn't before. And of course, the sort of the relationship to carbon is, I don't know about this. This is just, sort of an intuitive thing, but it seems like, as well as being a good use case for native, a CLI is usually a really carbon efficient way to do something compared to spinning up a browser and then bringing up an application with a ton of JavaScript and that kind of thing. So maybe we should be moving more towards CLIs. So with native, the what allows it to potentially save carbon is it has this magnificent elasticity. Going back to light switch op, sort of, it actually starts faster than a light bulb. So it starts, compared to turning on a light switch, starting native Quarkus is faster. That's really cool, but an app starting faster isn't elasticity unless you also stop the app. It goes back to that observation from Corey Quinn, elasticity doesn't mean just scaling up and then staying up. It has to be going down. So you have to have that organizational willingness and that automation to go down as well as up. If you have that, native can solve a lot of problems for you. So overall with Quarkus, it can reduce carbon sort of automatically, just because it uses less energy. These things are free, they're direct, they're easy to measure. It can also have these, what I call enabled behaviors. So this is really sort of a people problem. You have to take advantage of it. You have to make a change in how you do things to get the benefit. But if you do, there's potentially a big benefit. And so that's things like when you do your provisioning, go for a smaller instance, because Quarkus will fit. Or when you think about how you do just your workload management in general, be more elastic. Write your application so that it's designed to come up and down much more quickly because you can. And that, that's potentially quite cool and quite useful. So on that previous slide, I was talking about how Quarkus can help you save carbon, but actually it's not at all just about Quarkus. It's no matter what you're doing, it's really worth thinking about these things, elasticity, utilization, efficiency, make your code efficient in ways that it matters. And then finally, is what I'm doing useful? Should I even be doing this? And I think going back to this sort of question of, is it all terrible? It's actually, I think, kind of not only is it not all terrible, it's kind of the opposite. Because if you remember the Vroom model, which, to be honest, you probably don't remember the Vroom model because I mentioned it a while ago, but I made up the name. You've never heard of it before. You may never hear of it again. But with the Vroom model, it's really counterintuitive. This idea that if software goes faster, it's using less carbon. And I think that's because we have sort of a lot of the things that we interact with in our day-to-day life are the opposite. So a while ago, I had to buy a new car. And I had to sort of make this kind of painful choice because I wanted the car with a big engine that was going to go fast, but it was going to use like a lot of miles per gallon because it had a big engine and it went fast. With software, if software goes fast, if it has a high maximum transactions, that usually means the carbon per transaction is low. That efficiency makes it go fast, and it also uses less carbon. And this is kind of awesome because it means we don't need to make those same painful choices that I had to make when I was choosing a car, and this is sometimes called a no regrets solution. And I was trying to think of another name for this. And it's also sometimes called co-benefits, but I'm not sure that's totally clear. Sometimes I talk about the double win. Again, I'm not sure if that's totally clear. Sometimes I talk about win-win. And then I was trying to what can I do that's distinctive? I talked about win squared. It's sort of like 1 + 1 = 3. You could call it a twofer, but I think that only makes sense to American audiences. I'm not sure. Someone suggested that we call it an Überwinden, which looks like it's German, but actually, if you're German, several German people have pointed out this does not mean this in German. It just looks like it should. So this is another one where maybe only makes sense to audiences who can't speak German, or the extra win. And we've got an excellent question from Martin, which is, did we take into account the building of the native application as well? Because of course, if you build a native application, you will know you built that native application. You're sort of sat there watching it for a few minutes. And is that more or less carbon intensive than just a plain old Java C? I haven't actually measured it, but intuitively, given how long it takes, I think building the native application has to be more carbon intensive. It's doing a lot of optimizations up front. That's something that I want to look at. But to be honest, it went down my priority list a little bit when I saw just those charts that showed that the native application was overall, even at runtime, it was actually using more carbon, because then I thought, well, it's already using more carbon, so I don't need to add in to my calculation the extra carbon from build time. But you're quite right that in some circumstances, a native application is going to use less carbon. And so then we to do that calculation, also need to add in, okay, well, what about this increased build time? And definitely going back to only doing what you should be doing in your workflow, you probably do want something like what we have in Quarkus with dev mode, where you're not building your inner loop isn't necessarily including native compilation because it is slow and you don't want to be doing it 20 times a day. You get it working, and then you go and you do, your sort of secondary testing as a native application, both for your own quality of life and also for carbon efficiency. So I mentioned quality of life, and I think that's one of the great things about these climate solutions, which is like, it's not just that they're saving the planet, they can make actually everything better across a whole bunch of metrics. So if you think about the zombie servers that I talked about, where a quarter of servers were zombies, a different study tried to quantify how much this cost. It was just on public cloud spend, not even the things that are running in our own data center or the applications that the servers that got bricked into a wall accidentally and then no one knows about them, which is a story I heard. Just on public cloud, it was $26.6 billion that was wasted in 2021. If you think about what you could do with that money, that is so much money. And so then this goes back to the double win, which is that if we can find a way to turn these things off, it's going to save a lot of money. And we see this all across the board. So, for example, when we think about renewable energy, now renewable energy is 9 times cheaper than burning fossil fuels to make energy. So kind of, why wouldn't you want renewable energy? And we see this reflected as well in our cloud decisions. So for example, if you were to host in Montreal, that would use 88% less carbon than running the same workload in London, where I am. That's kind of awesome. That's a good reason to do it. And it's 15% cheaper. So why wouldn't you do it? Same thing, if you wanted to host it in Finland, that's 43% less carbon than London, and it's still saving you that I think I said that wrong, 43% less carbon than London, and it's still saving you that 15%. So why wouldn't you? And, we see this across the board. So I got the idea of the no regret solution from Jonathan Foley, who works with the Drawdown Foundation. And I find it so inspiring because what he says is climate solutions are just better ways to do the things we want to do. So like, unless you're a shareholder in a oil company or that kind of thing, the climate solutions, it's not, we have this idea of, I think, sort of, hair shirts and, suffering to save the planet, but it's not. It's using things that are actually better. So like, electric vehicles, for example, you can see in that tweet that he's quoting, electric vehicles get off the lights so fast. They're so satisfying to drive, and they use less carbon, and it's just all of this stuff. And I think we see this with Quarkus as well, that it uses half the carbon, and it's also really delightful to develop with. So, the application runs faster. It's just all better. So this sort of, I think when we think about sustainability, we shouldn't be thinking in terms of sacrifice. We should be thinking in terms of advancement. And that, I think, is good. So to sort of finalize, what should you be doing? Choose your hosting wisely. Don't host in South Africa. Probably don't host in Virginia. Use as people who consume IT, we have buying power. Our organizations have buying power. Use that buying power to encourage the businesses that you do business with to make greener choices. This is something that we can do. Turn your workloads off when you're not using them. Since we're Java programmers, choose an energy efficient framework. It will make a really big difference. And hooray, all of those things actually make us better off and happier, as well as lowering our carbon footprint. And this is something that all of us have a part to play. This is something that all of us can be doing. And with that, I think we can switch to questions. I know there was a question earlier about the link for the Principles of Green Software Engineering website. If you go to that QR code, which has the slides, on those slides, you can read off from the browser bar what the URL is. And I think as well, of course, Google will also just find it. So I'm looking forward to your questions. Thanks very much.
Thank you so much, Holly. And folks, please feel free to send more questions to Holly. And I really enjoy your talk to Holly. Thank you so much.
Thank you.
And I really like that light switch concept, right? That in which, yeah, it should be as simple as just turning off, and it should take care of all the things for you. And if you turn it back on, the context should be back as where you left it off. I think I love that concept. And yeah.
Yeah, and I think we just sort of instinctively, right? Like we have this dread of turning things off because we know that realistically it's probably not going to be as simple as turning off a light switch.
Right.
But it's good to have the aspiration, and it's good to have the mental model to say, okay, I know this thing is not like a light switch, and I know I am setting myself up for
Yeah.
a world of pain if I turn it off, but it should be like a light switch because I'm going to be better off if that happens. And it's like what they say with automation, you know, if it hurts, automate it. And so if turning your application off hurts, fix that by applying automation.
That's right. Yeah, we do have a question, or a question in here too from Yannicki. Yes.
Yeah. So I think because there's such a, so the question is, you know, what would be the next step after running your application in Quarkus? How do you make your application more efficient? And I think there's sort of two sides to this. One, it goes back to that sort of those four vowels. So the efficiency, the elasticity and utilization, which is sort of the infrastructure side, and then the efficiency and the utility. So we want to be looking, probably for this, you know, we're looking at that efficiency and utility side. So we improve our efficiency by running on Quarkus. And then after that, we can look at improving our efficiency more. So then we're going to be doing probably performance engineering. So the first rule with performance engineering is measure, don't guess. So you want to start getting some performance measurements in. If you can do it as a carbon measurement, that's great. If not, just an ordinary performance measurement will do. And find the bottlenecks, optimize the bottlenecks, and then keep going. And when we do performance engineering, all of us fall into the trap of the piece of code that we know isn't very efficient, that really irritates us, that we really want to refactor. We assume that we have to start there, but some pieces of code are very inefficient, but they're not run very often. So it doesn't matter that they're inefficient. Whereas maybe the piece of code that's really hot, even if we can only get like a 5% improvement in that code, it's going to make a difference. So we need to do the performance optimizations, but guided by data. And the other thing that we can do is to look at the utility side and to say, is every use of this application actually valuable? Can I be doing something so that I can give my users a choice, like to only stream the sound rather than streaming the video, or whatever the equivalent is for your domain? Can I make sure that everything that I do is useful, is making someone happy fundamentally? And if not, then maybe can I scale back that function, do that function less often? So instead of looking at the code level to do the optimization, we're looking at the people level to do the optimization. But thanks, great question.
Okay. So yeah, I think we have like a minute and a half or so. I guess at this point, because there will be the last session starting, you know, shortly. So I think if you have more questions for Holly, feel free to send Holly this email at this. Or actually, is this is your Mastodon?
Mastodon. Yeah. So I'm on Twitter and I'm on Mastodon. So Twitter is the first part, and then the Mastodon is the longer part. But yeah, definitely love to have a conversation about this and hear people's experiences as well.
Great. Awesome. Thank you so much. And thanks so much again, Holly, for this very thought-provoking and inspiring talk. And I think we should become more aware of when we're writing software, what do we use? The framework, the tools, everything matters. Yes, it's what it is. Yeah. So thank you. Yeah. Thank you, Holly.
Yeah. Thanks so much, Mary.
Yeah, thank you. And thank you everyone for having joined us today. And there's one more session for today. So we'll let you kind of get to the other session now. So, all right, have a fantastic evening if you're in Europe, or afternoon in the US, or in Asia. I think it's kind of nighttime or getting up. So yeah, wherever you are.
Yeah, I hope you enjoyed the middle of the night if you're in Asia.
That's right. All right, yeah, thank you. Bye.
See you all.
See you.